So Diego is really an entrepreneur in C++. He was so brave that he left a permanent position as a professor at the university to found his own ideas in a company and then joining a different company. That is quite strange.
But doing a package manager for C++, that's the actual crazy thing.
Oh, well, a package manager or the package manager. That depends on you. So, yeah. So thank you, Diego, for your support and for being here again. And let's see what you tell us about package manager.
Thanks very much, Jose Daniel, and it's a pleasure to be here again one more year. So yeah, today I'm going to talk about package management, but a very specific thing, which is the effort to try to standardize something in the package management area. So yeah, for those who don't know me, I'm Diego. I am the co-founder of Conan Package Manager. That means that I've been working professionally full-time in package management for C++ for more than a decade now. And I'm the project lead at JFrog now. I wanted to do this talk today because if we check the ISO C++ survey that happens every year, and they ask developers for the top 4 pains, those are these 4 pains, right? And all of them, they are around CMake, managing dependencies, build times, configurations, which all of them are very related also to manage dependencies, right? So it's clear that this is a pain. Sometimes it's a self-inflicted pain because not using a package manager, right? So in the same way, I'm not going to use CMake because it's not perfect. Nowadays, not using a package manager is more or less the same approach. Hey, I'm not going to use a package manager because they are not perfect yet, right? Or they are not standardized yet. The concept of a package specification is nothing new. It has existed also for decades. For example, we have the package config, we have the PC files there that they have been also for a long time, right? And we also have the CMake, both the find modules and the config files, config CMake files for managing dependencies, for specifying dependencies, right? Both of these approaches, they have problems. They are not great. For example, if we talk about the package config files, those are basically modeling always flags. Everything, including include directories, is yet another flag. And that makes it challenging to actually process, parse it, manage it at scale, or do automation around that. And config CMake files, they also have their own issues. For a start, it's CMake code, right? And CMake code is complicated. You cannot easily parse CMake code to deduce what is there and use it for kind of other tooling like managing or creating an SBOM, right? There are some talks from Brett Brown and about Luis Caro why these approaches are not enough, and we need to do better. We need something more, and this something more is the CPS. So the CPS, the Common Package Specification, is a very simple concept. We have a package, we have a dependency there. It might be already in our file system. We have the files there, and what we want is basically want to use this dependency in our projects. And we really don't care. We also like the freedom. We like to use different build systems, right? And we want the freedom to do that, but still we want to use dependencies in a kind of a standard way. So the CPS is exactly this. It's a file that specifies what's within a package. So this package can be automatically used, can be easily used by any build system. This is not a new thing either. The pioneer from this work was René Rivera. I don't know if René is here today. René? Hi, René. So he was doing the first proposal, up to my knowledge, to the committee called package format. There's also libmat by Vector of Bull. But then the actual name that we are using today, which is the CPS, kind of started some time ago in CPPCon talks that have been also proposed by CMake, Bloomberg, and also us. We have been pushing this name, this letter CPS, as Common Package Specification. Those are like good talks that can introduce you to the concept. Nowadays, the efforts are in this place. The CPS is a GitHub project that contains the specification. right? And there are discussions there, which is rooted in a paper that was also written by Matthew Wolke, which is the one that is kind of doing the heavier work of the spec at the moment. And also, we gather in 2 different places. In CPP Lang Slack, the ecosystem evolution channel is there. You can join it, and you can join the conversation. And there is also a Google group, which is a mailing, and we meet every month. Like the last Friday of the month, we meet together and we have a Zoom meeting to discuss the open items and keep pushing. And you are also, of course, very welcome to join this. In this, the good thing about this group is that there are important players. So there is Kitware with CMake there, is Microsoft, is Bloomberg. Brett Brown is kind of also leading and pushing ourselves. So the vendors that needs to implement these things are there, and they are actually implementing things. They are moving things forward. Okay, so let's have first a brief overview of the purpose and scope of the CPS. The idea is that any build system, when it's building something, it's building a library, right? It will output that library. It will output the compiled binaries for that library. But it can also create this file, the CPS files, that specify what is there, right? What are the artifacts? Where are the headers? Where are the archives, the shared libraries? If you have that, you have a thing that can be used by any other different build system. So in this way, the CPS is a way to achieve interoperability between build systems, and not only build systems, but any kind of tool around dependency management, package management, can leverage these files for automation. So that means that you don't even care about who is providing the dependency. Even if you have close vendor or someone is giving you a precompiled binary, that precompiled binary can come with a CPS file that will allow you to use that dependency exactly in the same way as you were building it, because you no longer care. It's a descriptor of what is there, and you can use it in the same way that if you are building it from source, even if it's a closed source binary. So the idea is that we have a compiled binary, so the CPS is not aimed for building things from sources. It just cares about you already have a precompiled binary. It also doesn't really manage the retrieval. So the package managers will still be there. It's just the specification of the thing once you have it there in your file system and ready to be used. The CPS files, we will see them later, are also for a specific binary. So you know in C++ you will have a different binary in Windows and in Linux. So the CPS file goes for that specific binary for Windows, for example, and you will have a different CPS file for Linux. It's focused, of course, in consumption of the packages, which means that it will define things like include tiers, library names, so the package can be used. And the specification itself, the current specification, already contains some kinds of ABI information about the package binaries. That is really kind of not mandatory today. The idea is that you can assume that the package is correct for your architecture. It can be used for your current build, and it's focused just on the typical information that the PC files contains, include tiers and things like that. Okay, let's see quickly how these files look like. This would be, for example, an example CPS file for the setlib library. The setlib library is pretty simple. We have a couple of headers there. We have, in this case, the static library of setlib in Windows. And that means that we will have our CPS files containing some meta information like the version, the license, the description, the website, right? But the important stuff starts with a prefix, which is the location of the package in our file system, right? The CPS file in this case doesn't need to be together with the setlib. In this sense, we can have a package installed in the system in USR directory, and we can have a CPS file elsewhere, even in our project, that just describes where the things are in our file system, right? And finally, we have the setlib component that actually describes this is a static library, the header is in this location, and the actual archive is in this other location. Of course, if we go to Linux, the file will be very similar, just the binaries will be in a different location, typically a different path, and the final archive will have a different name in this case. But otherwise, the file is very similar. One of the cool ideas about the CPS is that you can create the CPS file and put it together with your own binaries. And it can travel, it can go with it, and you can install it and move it around. For that purpose, you want to remove, of course, the absolute paths, and you want to make them relative paths. The way to achieve this is with a prefix. You define the prefix, it defines where the CPS file is relative to that prefix, and then you can use the prefix to make the relative paths for things like the include directories and the library location. You can make them relative to the prefix. Of course, if we change our dependency, in this case setlib, and we use setlib now as a shared library, that means that's a different build. That's a different artifact. That's a different package, right, that you want to use. You cannot link both at the same time statically and dynamically against setlib. You need to use one or the other, right? In this regard, you will have a different CPS file for this build of setlib as a shared library, which is similar to the previous one, but now we will have, first, the type is different. It's no longer an archive. It's a dynamic library. And then for Windows, we need two things. We need both the location of the shared library, the actual dynamic library, and in Windows, we also have the import library, right? The import library is defined by the spec, by the link location property in our JSON file. Then you know that there are packages, there are many projects out there that they do not contain just one library. They might contain more than one library. For example, libiconf. Libiconf contains two libraries, iconf and charset, which depends on one another. It's very naive that the project will split into two different projects just because one project should be one library. That's not going to happen. That means that our CPS needs to model multiple libraries within the same package. And the name for that is very similar to the CMake components, and is the components property in our CPS file. In this case, we have two main components, which are the two archives. You can also create kind of artificial components. In this case, what this CPS is modeling is say, okay, the headers are common for both libraries, are in the same location, so I can have like a common libiconf interface component there that only contains the include paths. And then I will have two archives components, one for iconf itself and the other for charset. And the way they are connected is via the requires field. Right? The requires field will define, for example, that charset depends on the other. So whenever you are linking with charset, it will automatically bring iconf, and both of them will depend on the libiconf that brings the headers definition to both of them. One of the cool things about the required things is that it's not only for internal components within a package. So if we have, for example, the flag package, it has a dependency to another external library, which is called OGG, right? So the requires field can define, hey, this specific component within this package has a dependency, a linkage dependency to the OGG package, which is external to this CPS. Hopefully, there will be another OGG CPS file somewhere that defines this component in order to be used. And here, I didn't want to do like a complete overview of the spec. I'm just trying to introduce some ideas, some concepts. For example, the definitions. There are many libraries, many packages out there that in their headers, they have some preprocessor definitions that are necessary. In your consumer project, you need to define this definition, otherwise it will not work properly, right? The idea is that the consumers project, they don't have to figure out, they don't need to read the documentation to bring that. The CPS will find, hey, you need to define this, and this definition will come automatically into the consumer's projects, so it transparently is able to use flag in this sense. There are certain packages there that depends on system libraries, typical the pthread, and Windows, the sockets, the WSOC32 library, things like that, right? That doesn't necessarily need like their own CPS themselves. So you can define that a file, a component, a package has a dependency to some system libraries. That means that when a consumer, in this case, is using libflag, they will also need to link with the -lm library, right? And finally, the language, because there are packages out there that have a C header interface, right? But under the hood, they are implemented in C++, which means even if you are not aware of this because you are linking with a C header, right, you need to link with the standard C++ library. Right? That's a typical linkage error, happens all the time because the consumer doesn't realize that they need to link with the C++ standard library. The link languages defines that. If you are linking with this, in this case, if you are linking with the libflag++ component, the C++ binding library there, you will need to link with the C++ standard library because it's using C++ and under the hood. Whatever. Okay, so that's just a quick idea of the spec, right? What I really wanted to do today is show you and demo that this is not just a spec. This is a reality. This is happening today, and there are implementations. And I'm going to demo these implementations today. I'm going to do 3 demos. I'm going to start with this one. I'm going to do like a round trip of CPS generation and usage within CMake. So CMake, it said they have already implemented the capabilities of generating, writing, and using CPS files for their libraries, right? In this sense, I will have like a library, it's called my package, right? I will be building this library, and when I build this library, it will generate for us the CPS files automatically, right? And then I will use this library in another application to create an executable, right, that will consume this library via the CPS files without any config CMake file at all. Now let's see if we can manage to do this. This is the risky part. You know that I like to do like live demos, but this is risky, especially with this thing here. Jose, we need to fix for next year. It's really challenging to type here. Cool. Okay, so here we have the library, which is just a header here with a my package function, and the implementation of the function is also trivial, just printing something to a screen. So it's a very simple library, hello world-like. The important stuff is here, right? In CMake, now at the moment it's experimental, which means that we need to define this variable here, it's a gate. They basically don't want us to use it in production. That means that if you want to use it, you need to define this, and you can see the value here is horrible, it's a UID, and it will change every release, just to guarantee that they will break you, so you are aware that you cannot use this in production, right? But otherwise, it's just a variable that you need to enable, and then you will get the functionality. The rest of the CMake list is standard CMake. There is nothing specific here. The only change that is necessary is this new keyword, which is the package info keyword, right? So when we are doing the install of our package, we specify package info, and that's all we need to generate CPS files for our library. Let's see if we can do that. So we are going first to create configure the project. It might be a bit slow in my Windows machine. Okay, the project is configured. Now I'm going to build. There is nothing related to CPS yet. So that's a regular build of my project. Sorry. And this is building the actual library, right? And now is where the stuff is going to happen. I'm going to CMake, I'm going to install my project. Install this build. I'm going to put the things in the install folder. And what I'm doing the release config. Okay, and now we see the messages. We see that the header is being installed, the library is being installed, and also 2 files are being generated and installed. That means that if we spec now our project, we can see that we have the install folder. The install folder contains the actual artifacts, the header, the archive for the library, and it created a CPS folder for us with 2 files, right? And you recognize the fields that we have seen previously in the spec. We see the includes there to point to our headers, right? This is an archive, it's a static library. You can see that also the files are actually split in 2 different files, like the base one and the release one. Basically, you can merge the 2 JSONs and you will get a single file. You can either express in 2 files separated or in 1, as you wish. But CMake is generating them in the information spread in 2 different files. And this is what we need, just the location of the static library defined there, right? But the important thing is that there is no CMake code at all in this folder. Now, if we move to the consumer application, this is a very simple main, right, that is using our library. And the CMake list is also very simple. The only thing that we need to do is to enable the feature. This is a different UID, right? It's yet another gate to make you painfully use the feature. But otherwise, it's just a fine package. And it's the typical executable and targeting library. Nothing changes there, just enabling the feature. And if the CPS file is in the prefix, then CMake will be able to use it. Okay, so let's try CMake build. And the thing, what I need to do here that is special, I need to specify the prefix path so my other project, the CPS files, are found, which means CMake prefix path, and I'm going to point it to the other folder that contains my dependency and contains the CPS files, which now I can build, and I should be able to run my application, the app application that depends on my package, right? And the magic of all of this is that there is no CMake code at all in this. It's just the CPS JSON files that have been used to consume this dependency. Okay, the second demo. You will say, okay, but this is going to take a lot of time. Why? Because we need the whole ecosystem to start generating the CPS files for us so we can use them, right? Not really, because there is already a lot of information out there. For example, we have Conan packages, right? And in this demo, I'm going to use 2 Conan packages, setlib and bzip2, that are already existing in Conan Center, right? They do not contain the CPS files yet. Right? But they do contain enough information to generate the CPS files on the fly for these packages. So I can use these CPS files in a CMake build exactly as I did, to consume 2 typical third-party packages that someone created before, even before they knew about the CPS specification. The thing is that Conan contains this information already in the recipes. So every package contains there a package information method that contains the equivalent information of the CPS. It contains include directories, library names, basically the information that you need to put into the CPS file. So the information is already there. So if I convert this information to JSON files, those are CPS and can be used by the system. The cool thing is that Conan Center, for example, contains nowadays like 1,800 different recipes for multiple versions, multiple binaries. That means more than many hundreds of thousands of binary packages. Every one of these packages can generate today a CPS file that can be tested by implementers of the CPS specification. And that is a huge knowledge base that has been created by the community, like with many thousands of pull requests. For example, in 2023, we got around 6,000 pull requests just to contribute knowledge to the package database. And we don't need all build systems to implement CPS, right? These packages in Conan Center, they are built with auto tools, with Meson, right? We don't need auto tools to implement CPS. I don't think this is going to happen anytime soon, right? But we have already the information there to generate CPS files for auto tools projects. Okay, so let's move to the folder. I'm going to show you the code. Right. So here I have my application, which is depending on setlib and visit2, just printing some information, very simple. We have a CMake list that is basically the same CMake list that I showed you before. It's a CMake list with two find packages, one find package for setlib and another package for visit2. And we have just the gate there. So what I have here is, in this case, a Conan file, right, that allows me to install the dependencies and generate the CPS files for me. So I can do here a Conan install. It will bring the dependencies, which means it will be generating on the fly the CPS files for both setlib and basic2, right? And with these two files, I can perfectly now do the CMake I need to specify the CMake prefix path. The project will now find the two CPS files for setlib and basic2. So I can build the project, and I should be able to run the project using both setlib and basic2 from Conan Center via CPS files as well. Finally, for the last demo, what happens for build systems that do not understand CPS yet? For example, Visual Studio, right? CPS files can be very easily mapped to properties files in Visual Studio. And this is what I'm going to do right now. First, I have a Conan package that I can create. There's nothing special here, just that this Conan package will contain the CPS files inside the package. So here we can see that the CPS files have been generated and they have been put inside the package, right? So when I move to my project, this is just a very regular Visual Studio solution. Just the solution, the project, right? The Conan file to install the dependencies. And when I'm doing a Conan install here, sorry about this, we can see that Conan will install this package, will install the dependency, and it will create properties files for us. It can easily create things like this. If you realize this is just XML properties file that contains the same information of the CPS, the include directories, the library names, whatever is necessary, from the CPS file, JSON file, to this XML format, which in practice means that I could open the ID, sorry. And I could be building my, I could build and launch my application using the dependencies from CPS files that have been mapped to Visual Studio properties file. Okay, so to finalize my presentation, this is still not perfect. There are open issues. We are working on that. There are things like the transitivity is still not great. There are issues with that. We are also the naming using uppercase, lowercase, it has problems. But we are working on that. We aim to have more progress for CPPCon this year, and we will increment in the knowledge base. So to finish, I would say CPS is an important effort towards standardization. It already has implementation, right? As you can see, this is working. It's working today. right? And it's very promising. This will help a lot around using packaging, tooling around build systems and things like that. And the call for action here is, we need you. This is an effort. The more usage, the more testing, the more feedback that we get, and it's very easy to join. Just go to any of these places, and we will welcome you there. Thank you very much.
Thank you very much. I think we have time for a couple of questions. Otherwise, you will reach Diego in his booth.
Thank you very much for the talk, Diego. And so this is basically like a way to get rid of the all config CMake files and find whatever library files.
Exactly. It's a way to get rid of that for many reasons. Those files are very difficult to generate correctly. Indeed. For example, the transitivity of config CMake files is not easy to achieve. So if we can get rid of that, it's not only we are making things easier for dependency management, we can get the CPS files for our dependencies, and we can generate an SBOM, for example. And there can be many other things that we can do if we standardize just moving from CMake files to JSON files with a standard format. It's basically the idea.
Perfect. Thank you very much.
Thank you.
So one of the last things you said was that the MS build, the XML file, had the same information as the CPS. Yes. Why we need a CPS then? Why don't we get the XML file and use that and standardize that if it already exists?
Because it's XML for a start. Yeah, this is not
good reason.
It's also very proprietary from Microsoft, which is, I mean, I think it's a great tool. The properties files of Microsoft Visual Studio are surprisingly powerful. I've done incredible things with them, so it's a good tool. But I think being proprietary for Microsoft is kind of a blocker in that sense.
Thank you, Diego, for the talk. My question is about cross compilation. How you deal with cross compilation with CPS? Yeah,
that's a good question. So the CPS itself doesn't really care much about that. Let's say that you are cross building an application, right? And you depend on setlib. Setlib itself has to be cross compiled for your target platform, right? So the idea is that you launch the build, and the CPS is not covering that. You launch the build yourself for setlib with your cross compiler. That will generate the artifacts for your target architecture, and it will generate a CPS file that defines the location of those artifacts. If there is some extra flag, compiler flag that is needed, like -M64, whatever, it might be added to the CPS file itself. So when you are launching the cross build for your consumer application of those dependencies, it will bring the information from that dependency that has also been cross compiled. So the process it doesn't really care about the architecture of the dependencies on the package that you are bringing via CPS. The spec might contain like ABI information. So if you bring one incorrect architecture one, it might give you an error. Hey, you are trying to pull something that doesn't match your target architecture. But just an extra thing, extra bonus is not mandatory for everything in CPS at the moment.
Okay, I'm going to thank you at this point so that we have time for Luis. Thank you.
Thank you.